Brad Williams, Frugal Finance. Let's just dive into this, okay? The term structure of interest rates can be overwhelming. In other words, there has to be pricing related to swaps. And I introduced this long ago. It's called bootstrapping, and we're going to use zero coupons. I'm not going to spend a gazillion hours explaining this. If this information here, and this is what you have to use in order to price a swap, if you struggle with this information, go back, take a look at my continuous compounding course or future zeros, that course, and I explain all of this in detail. Here's the other bit of a challenge. This is a summary. As we move along, I'm gonna have an actual pricing format. You'll see it when we get there. Ultimately, what's the goal here? We have to match this swap fixed rate. This swap fixed rate has to equal the forward rate. And the only way to do that is, well, we just have to crunch a bunch of numbers. So with that being said, I'll show you what's going on here. It's not difficult. It's just extremely time consuming. I know there's going to be programs out there, applications that take care of this for you. But what if, and here we are, the end of July of 2024, and over the weekend, Microsoft blew up. It wasn't their fault, but the fact is, as we move further and further down the road, we're going to see more widespread outages in the software sector, period. And when that happens, you're going to be sitting at your desk and there's going to be a Microsoft blue screen with a sad face. And you're going to go, what do I do now? What you do now is you open up this example and you start crunching the numbers by hand, like I did. It's not difficult. Or you're just going to copy paste this and start working on it while everyone else is just looking at the screen going, well, what do we do now? You're going to be proactive. You're going to use this information and solve some problems and get that extra bonus. Bottom line is, don't rely 100% on someone else's work. Do your own verification, do your own research, do your own number crunching. I know, in one ear, out the other, but that's okay. I just mentioned it. So in this section, we explored the term structure of interest rates, relationships between term to maturity of bonds and their respective yields. Analyzing the term structure of interest rates requires focusing on bonds that are as similar as possible except with respect to maturity. Consequently, term structure analysis avoids attention to bonds that differ in the tax status, default risk, callability, and coupon levels. Table 19.2, I didn't show it, shows data for certain periods in tabular form based on bonds selling at par. Therefore, these data express the par yield curve, the relationship between yield and maturity for bonds selling at par. Starting with data based on the term structure of par bonds, which are published daily in sources such as the Wall Street Journal, it is possible to derive other yield measures that will be important in understanding interest rate options. We're particularly interested in the zero coupon yield curve and in the implied forward yield curve. We've gone over this a couple of times, but I'm going to show you how it works. Remember that? And if you didn't take the interest rate options, if you did take it, and we were looking at SOFR and we were looking at section 16.9 or something like that, and I showed you, well, here's this long series of numbers and this ugly looking equation. That is going to be something like this. Doesn't that look really familiar? Doesn't this look like that 16.9? It's going to be, because all we're doing, we're going to go backwards and look forward. What do I mean by that? In order to compute the zero, we're just going to have to use this formula repeatedly over and over and over again in order to come up with the zero coupon. With that being said, I'm going to shut up and I'm going to explain to you where we're going. Starting with the data, we're particularly interested in the zero coupon and in the forward yield curve. The zero coupon yield curve expresses the relationship between yield and maturity for bonds paying no coupon payment over the life of the bond. A forward rate of interest or forward rate is a rate of interest for a period that begins at some date in the future and extends to a more distant date. Well, how are we going to get that forward rate? For example, a forward rate might cover a period beginning 2 years from today and extending for 3 years to a time 5 years from today. The implied forward yield curve expresses the relationship between term to maturity and rates for forward rates as implied by the par yield curve. All of these interest rate relationships, the par yield curve, the zero coupon yield curve, and the implied forward yield curve, form a single system of mutually consistent interest rates. Given one set of rate, it is possible to find the others, as we now show. It's a way to show the connection between zero coupon spot yields and the time until they mature, all based on a specified date. The zero curve, as opposed to other kinds of yield curves, represent a set of yields unencumbered by complicating assumptions about reinvestment rates for coupons received before bond maturity. As a result, practitioners can be confident that the discount factors and the expected forward rates derived from zero curves do not depend on any reinvestment rate assumptions. Because of the desirable properties that it possesses, the zero curve has become a key ingredient to the valuation of many financial instruments, including swaps. So zero curves come in many forms depending on the interest rate class and currency. With US dollars, we focus on the SOFR zero curve. It's worth noting that zero curves aren't just picked from thin air. They're carefully designed because real zero rates are only available for a select few maturities. For the rest, they're constructed using a mix of bootstrapping and interpolation methods. Wow, it's all coming together, isn't it? Any coupon bond may be regarded as a portfolio of zero bonds. Each cash flow on the coupon bond is considered to be the payoff from a zero coupon bond. Therefore, we can express the value of a coupon bond as follows. Equation 19.2, P is equal to sum of M, C divided by Z, where P is the price of the bond at time equals 0. C of T is the cash flow from the bond occurring at time T, and Z is the zero coupon factor for a payment to be received at time Y measured from time of T, time of X. Equation 19.2 is the same as the familiar bond pricing formula, except that it allows a different interest rate to be applied to each payment on the bond. Table 19.3 presents the U.S. Treasury bonds from the par yield curve, all with an assumed par value of 100. Table 19.4 shows the cash flow from each of the bonds in Table 19.3. From these, we show how to compute the zero coupon yield curve and the implied forward yield curve. Based on Table 19.4, we have the following, where the subscripts AV on the price indicates the bond, since we are finding all prices at time 0, and the subscripts on Z are expressed in years. Here we have this number here. These are fixed, okay? This number is going to be, this should be yellow. That means you're inputting this information. The par, this again is something that you're going to input. Here's the maturities. We've gone through this before. So I might be a little short in terms of my explanations. And again, you can go back and take a look at the other explanations or courses that I present. We have this cash flow from treasury bonds. We're going to take D44 right here, and we're going to divide it by 2. We're going to take D45 divided by 2. Why? Are these not semi-annual payments? We have bond ABCD, and then we have this, what happens here? It's going to mature, and we have 100, 100, 100, 100, 100, 100. In the end, we have this cash flow of treasury bonds. We're going to come up with this 7.12. Looking at table 19.4, it looks like we have a price of 100, 0.064, et cetera, and then a price of a yield of 7.12%. And I'll delve into this in a minute. So we have the 6-month, and here is the formula. Isn't that this right here? Yeah, 19.2. All we're going to do is use this and extend it out. This is what it looks like as we go from 6 months out to 3 years. Then what we're going to do we're going to end up computing the swap rate. So we're going to use D44. We're going to go up here and use this 5.8, divide this by M58. Then we're going to use the bootstrap method. And we have 102.9, and that is derived from 102.9 right here. And then we're just going to use, again, we're using this same methodology. Here we're going to take bootstrap zero rate coupon factor. We have 1.029. Then for year one, it's going to be 103. Then we're going to go 100 minus 3 divided by 10.29. That's how you bootstrap this thing. You go down one and then back up one. All right, what do I mean by that? We're using 2.9 and 3. So we're going to go 103 and then 100 minus 3 divided by 1.029. That's 1.209. Then we're going to, and again, here's the formula. Then we're going to do the same thing over and over and over again. So then what we do, we have to look at this information, and then here is, we have to compute the zero annual yield with continuous compounding. We have one, and then this formula is probably noted down here. I'm just going to give you an overview. We're going to have 1 log normal, 1 M58. We have this bootstrap 0, and we have to have this annual yield. So we have 5.63, and we're going to follow this through. This is just verification. If you go back up here, 5.8 and 5.63, we have an equivalent situation. The equivalence is going to be 580. And then our pricing 96, and then we have this trial and error issue, which we're going to use to probably price this. We're going to price, okay, this is the swap fixed rate. Get used to this because we are going to make sure the swap rate and the forward rate match. This D44, I will explain all this in a bit. We're going all the way back up here. We're going to take this D44 minus M58, which is going to be your coupon, this bootstrap, plus D45. We're going to go down here, and all we're going to do is plug and chug in order to come up with this swap. So this swap should be priced at 6.2349. How do we compute the implied annual interest rates? Let me explain. With a 6-month zero coupon factor of 1.029 right here, the implied annualized yield, assuming semi-annual compounding, is 5.88. Remember, I said we're going to compute this number. So we're going to have 5.88 right here, 5.88, 102, 1029. We next find the 1-year zero coupon factor by treating the 1-year coupon bond as a portfolio of zero coupon instruments. The 1-year bond consists of payments in 6 months of $3, half the annual coupon rate, plus a second payment in 1 year of 103. The par value plus the final semi-annual coupon payment is going to be equal to 106,093. So here it is right here. We're going to use the same format. If you look at this formula, what are we doing? This is just a different computation, but 103, 100, so we have 10629. In essence, we've begun with a short-term zero coupon instrument, found the zero coupon factor, and used this initial factor to find the factor for the next short term. The process is called bootstrapping, the sequential process of using short-term rates to find a longer-term rate. Got that? I know, it's a little bit confusing. All we're doing is we're just discounting, and then we have to go back and use the previous zero rate in order to find the forward rate. Continuing the process of bootstrapping gives Z is equal to 0.105 is equal to 109,9346, and Z, the next one will be 14386. Notice that we are stymied at this point with respect to instruments in table 19.3 and 19.4. Our next desired factor would be Z of 2.5. However, we do not have the price of the bond maturing at T equals 2.5. See that? 2.5. What are we going to do? Also, we cannot use the bond maturing at T of 3 because it has an intervening payment at t is equal to 2.5. Therefore, bootstrapping requires an instrument maturing at each date up to and including the longest maturity date for which we wish to compute the zero coupon factor. Note also that all the bonds in table 19.3 and 19.4 are traded at par. The bootstrapping technique could be applied to bonds and that are not at par due to a diversity of coupon rates. However, differing coupon rates can affect bond yields, so it's best to use par bonds only. The set of bond yields we've been considering also implies a set of forward rates on interest. Let f of r, x of y indicate a forward rate of interest to cover the period that begins at future time x and ends at a later time y. Also, let f of r, x of y be the forward rate coupon factor to cover the period that begins at future time x and ends at a later time y. Given the zero coupon factor, any f of r of f can be found as f r of f is equal to z of 0 y divided by z 0 of x using the data in table 19.3, table 19.4, along with zero coupon factors already computed. We have the following. We're going to go right here. We're going to see, notice the timeline here. This is 6 months. This is, this would be period from 6 months to 1 year. This is 1 year to 1.5 year. This is 1.5 year to 2 year. This is 6 months to a year and a half. This is 6 months to 2 years. And this is 1 year to 2 year. So there's your FR of F. Now look at the numbers here. I may need to split this screen. View, split, and then I'm going to bring this here just so we can try to match this information. We know this 1.301 here. If we do this, might have to do it this way. Got this 1.301 as computed right here. We have this forward rate 1.310. Okay, notice the timeline, 6 months. Then we have 1 to 1.5, 1.3621, 209 plus, and 104.046. I don't think we're going to be able to find this one. 1.0683.874. Okay, got this? Notice the timeline of 1.5 years here, and then we have 1 year here, and we have 6 months here, and this is how you compute this stuff. We have to go, we have 0 forward and 1 year and 1.5. Then we have this 111, and then we have this 1078, which is not computed here, but you kind of get the gist. You have to do this for, there's 6 months. There is the first 6 months. There is the 1 year. There is 6 months, 1 year. Now you go up here, we look at log normal M58 right here, and then we should M59, annual yield 1.64169. Okay, log normal 1 plus M62. Given the various FRFs, the forward rate, the FRs are the interest rate implied by the forward rate factors. By using FRFs, you can make computations based strictly on cash flows and then move to forward rates under various compounding assumptions. In the example data on tables 19.3 and 19.4, the yield curve is upward sloping with longer maturity bonds having higher yields than short maturity bonds. In this situation, the zero coupon rates are high than the rates on a 2-year zero coupon bond. For example, assuming an annual compounding, the zero coupon interest rate on a 2-year zero coupon bond is 6.4948 right here, compared to the yield of 6.8 on the coupon bond right here. Forward rates map onto these spot yield measures only approximately, but for the same example, the forward rate interest rate to cover for 1 year to 2 years, 7.8134%. Leads to the following rule. Forward or upward sloping yield curves, forward rate greater than 0, greater than coupon. Downward, forward, less. We will use the bootstrapping technique in the various measures. I'll explain more of this down the road. This is an introduction to bootstrapping. It's sort of complicated in that there are so many different moving parts. We start off with this annual, then we break it down to cash flows, Then we break it down to find the zeros, and then we break it down by term. Then we compute the zeros based on a specific formula. This is just this number, the numbers here. I just grabbed those. And then last but not least, we have a price of 96, 1068. So this is trial and error, and this is a little premature. I'll explain all this later. And then ultimately we have this. This should match this, and it does. All I did was duplicate this information. Brad Williams, Frugal Finance. Thanks for watching.